Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. We are continuing with X-ray diffraction. We are in module 11 and this lecture will again discuss about the intensity of diffracted beams. So, the previous lecture we have derived structure factor expression and we have discussed the structure factor, what are the conditions of getting something like diffracted beam from certain crystallographic planes. We have seen that condition, we have developed the condition for simple and then base centered, body centered and face centered crystal structure, and we have seen, we have told that the conditions because of which certain intensities, which are known as the forbidden reflections, are missing in case of body centered, in case of face centered those crystal structure, and how we can utilize this in order to study something, for example phase transformation. And also we have discussed about the general nature of structure factor calculations, that this body centering or face centering, this is independent of the crystal structure that we take. So, in this class we will continue with that and we will discuss about the structure factor calculation for a more complex crystal structure like NaCl. We will take one, and then we will see the intensity of X-ray diffraction in a real specimen, what are the other factors that this intensity, X-ray diffraction intensity depends on in a real sample, and we will try to discuss about at least multiplicity factor, temperature factor, possibly in the next class we will discuss. So, we will continue with our discussion about the structure factor for more complex crystal structures. For examples, so until up to now we have discussed or we have derived the conditions for 4 different structures, and those 4 is like simple, body or base centered and body centered and face centered. So, here the maximum number of atoms that we discussed is 4 in case of FCC. Body centered is basically we discussed about 2, base centering again we had only 2 and simple one only 1. So, what if the structure contains more number of atoms than this? So, more number of atoms than 4. So, those kind of cells like will be in such a way. So, the atoms, if the unit cell contains more number of atoms than this FCC than this face centered condition, then we will have some additional restrictions on the diffracted beam intensity. So, diffracted beam other than this, for example, if we derive like face centered, the conditions that HKL has to be even all unmixed. In this condition, on and above this condition, will have some other conditions for getting intensity, or which will be modifying the intensity of beams from certain crystallographic planes. So, that we will have further restrictions, or the intensity of those beams will be further modified. Okay. So, for example, if we look at this diamond cubic structure, this is the silicon, best known example is silicon diamond cubic. So, diamond cubic unit cell is the base, basically it is a FCC structure, and then additionally we have some other 4 other atoms within the unit cell, which are basically present in the tetrahedral void positions, half 1/4 and 2/4 and 3/4 position, 1/4 and 3/4 of body diagonal. So, these positions we have additional atoms, and out of the 8 position only 4 are there. So, this is the diamond cubic structure. So, diamond cubic structure best known example is silicon, and in diamond cubic structure we will have corner atoms plus 3 face centered atoms plus 4 additional atoms. So, altogether it has 8, effective number of atoms is 8. So, in diamond cubic structure we will have like this is the typical FCC structure. And in this case, in addition to that, we will have some other reflections like 200, 220, 420. This kind of reflections will also be absent. So, we will be having the same that unmixed. So, the mixed one, in this case the mixed one will be absent for, because it is basically an FCC structure. So, this restriction will be there for diamond cubic structure, for silicon structure. This restriction will anyway be there, that mixed reflections in any case, like for example 100, 110 and so on, this kind of mixed reflections will not be there. So, that will be the same as FCC. But because of the presence of this additional 4 atoms here, what we will be not getting, we will not get some more reflections from for example 200, unlike this normal FCC where we have after 111 we have the second one as 200. In case of silicon, after 111 we will have the next one as 220, which is here. So, this 200 is completely absent in case of diamond cubic because of those 4 additional atoms. The structure factor gets modified even more. We are not going in the exact form of that structure factor determination. You can try that at home as an assignment, but we will find out that not only mixed unmixed condition, there will be far more other condition. Basically, one of those conditions I was discussing in the last class, if you remember, even within the mixed condition, 2 even plus 1 odd versus 1 even plus 2 odd. What is the difference between that and there? This diamond cubic structure, that will be very important. You can try that. Okay. So, but the fact that in case of a diamond cubic structure, this basic condition is valid, the mixed condition, mixed unmixed condition is valid. That means, if it is a mixed, then you will not get intensity anyway, whether it is an FCC, whether it is a diamond cubic, you will not be getting the intensity. So, that itself means that this lattice is by default, it is a FCC. So, the base is FCC, and on top of the FCC structure there are more modifications because of extra atoms present. So, that if we solve, if we get anything like this kind of reflection, then we know that okay, we have to start the atomic unit cell. If we want to construct the unit cell, if you want to solve the crystal structure, we should start from something like an FCC unit cell, and then on top of the FCC unit cell, because of some other restrictions, we have to put some other atoms in proper place. So, that is how the structure factor for this complex systems is again related to their unit cell or the atomic arrangement within the unit cell. So, we will take one specific example or more famous example here that will make this what we are discussing more clear, that that on top of FCC crystal or FCC structure factor relation, what other factors or will come and modify the intensity. Okay. So, as it is shown here, this is the atomic positions for sodium and chlorine. Okay. So, this is sodium. If you consider only sodium, this is an FCC. So, we have this as the sodium. So, the green balls are sodium, and sodium itself has its own FCC structure, proper FCC structure. Now, chlorine, if we consider here, chlorine will also have its FCC structure. Basically, chlorine lives in the position of octahedral voids, which if we join the sodium, the chlorine atoms here, we can construct another FCC lattice in this, from this. Of course, we need some other unit cell on sides, then we can join and we can construct an unit cell, FCC unit cell of chlorine itself, and in that case sodium will be in the octahedral void position. So, whatever it is. So, basically what we can call that sodium and chlorine both forms their own FCC structure which are interpenetrated, and sodium position of sodium and chlorine is quite interchangeable. Okay. So, phase centering translation, again you have for chlorine sodium position you have the phase centering translation, chlorine positions also you have the phase centering translation. If you just you have to, the nature of this phase centering translation is a little different. So, you are just add the phase centering translation with this, what you are getting is this one, you are basically shifting the origin, you can shift the origin. So, if you just add along with that, you add this phase centering translation, half half 0, you are getting basically 0 0 half, this will become 1 1 1, that you take that as a origin shift and you will be getting this again this one. So, chlorine, and that is why I say chlorine and sodium positions are very much interchangeable, but that is okay. Let us not go into there, and let us try to solve this particular problem of NaCl, structure factor of sodium chloride. Okay. So, I write again structure factor F for this complete sodium chloride NaCl structure. Then I write the here the question comes, sodium and chlorine, I have two different type of atoms. So, their atomic scattering factor will not be the same. I can write one as sodium. Now, here the point is, actually sodium, structure factor of sodium is not equal to or atomic scattering factor of sodium is not equal to atomic scattering factor of sodium N plus, because Na plus is what we are getting in NaCl. There is a difference. Basically, here there is one electron is removed from here, and that is why it has gone to the ionized condition. Same way chlorine has received one electron and it has gone to ionized. So, that means the atomic scattering factor of sodium atom, pure sodium atom, and sodium chloride Na plus ion is not the same, but anyway we are not considering that, we will just be writing it Na, whether it is Na plus or Na, we will write atomic scattering factor of sodium. And then we know how to get that later part, the phase part, and we are writing it as 1 plus E pi I. So, this is typical for an FCC, the one that we have already derived. So, plus E pi I into K plus L plus E pi I into L plus H. So, this is what the expression for sodium, and now we have to write the expression, similar expression for chlorine, and that will come a little different because of the atomic positions, or you can interchange also because of the atomic position, it will be little different, but ultimately it will boil down to the same. We will see how. Okay. So, this one will be pi I into H plus K plus L plus E pi I into L plus E pi I into K plus E pi I into H. You can put all of this and you can find out. Okay. Now, from this, so this is the entire structure factor for this sodium chloride structure, and this two looks quite different, but they are not. We will see how. Okay. So, basically what, if you remember what I said here is that sodium position, sodium and this chlorine position, sodium positions are related by this phase centering translation. Okay. Here you can see this is what I discussed. This, if you apply the phase centering translation, this one, then sodium positions you can get it same as chlorine position, and they are also interchangeable. So, what we can do is that whenever a lattice and unit cell contains a common translation, which is in this case is phase centering translation, both sodium contains a phase centering translation, chlorine contains a phase centering translation. So, if this kind of a common translation exists in the unit cell, then we can factorize, we can take a factor, common factor in the structure factor calculation. During structure factor calculation, we can take out a common factor out of this. How to do that? I will show. So, we will write the same, this structure factor F, but now we are taking a common factor, and that common factor in case of chlorine we will do. We will not touch the sodium part, we will write the same thing, that is E pi I into H plus K and plus E pi I into K plus L plus E pi I into L plus H here, right. What we will do for chlorine part, we will take a common factor out here like this, H plus K plus L here, and this will give us here what will be left is this 1 plus E pi I into minus H minus K plus E pi I minus H minus L plus E pi I into minus K minus L. Okay. If I take this common factor out here from this expression, so this is what is left, and remember we have already said this E n pi I equals E minus n pi I. This is an important relation. During when we were discussing about useful relation, we said this is how the complex conjugate or complex in complex numbers, this relation is valid. Power series expression of complex number, this relation is valid. So, if we take that relation, what we can just do it here, we can put it back here, and what we can get is basically this again this entire term we can take, this will become the same. So, we will just remove this. Okay, what we will do is that we can, in order to save time, we can remove this, we can remove this, we can remove this. Okay, so then what will it become is basically H plus K, H plus L and K plus L. Okay, so then we can take this part and this thing becomes the same. So, that means what we can take, this common part we can take it out, we write E pi I H plus K plus E pi I K plus L K plus L plus E pi I L plus H, this is the common term, and then the rest of the term F Na plus F chlorine into this term, sorry, E pi I and H plus K plus L. Okay. So, this is exactly the same part as the face centered case. So, this part represents to the face centering translation, correct. So, this is what we have discussed during when we were deriving the face centering, the structure factor for face centered structure, there the same term appear. So, this is related to the face centering translation, whereas this is the new part which is coming because of this special unit cell where two different type of atoms are present and both of them are kind of interpenetrating. So, we are considering the entire unit cell. If I consider the entire unit cell, this is the basis part, this represent the basis part, sodium in the FCC and chlorine in another FCC, or sodium and then octahedral void positions chlorine. So, that kind of an unit cell is this is represented. This is the simple FCC or face centering translation. This part represent FCC translation. Okay. Now, how do I solve this thing? This one is known to us, that how to solve this one. So, let us first imagine what will happen if HKL, when we will get no intensity. Let us first derive that is easier. So, if we do not get, if we get HKL mixed, we have already seen this in case of an FCC cell. So, if HKL is mixed, this part is 0, ultimately F will also be 0. So, HKL mixed condition, we will not get any intensity for that particular plane. For example, we will not get anything from 110 or we will not get anything from 100. In that way, it is similar, it is same as normal FCC, right. So, that says that this is basically an FCC unit cell with some other kind of modification. What is that modification? That we have to see, and for that this will be another, this will add additional conditions in this structure when HKL is unmixed. So, that we have to now consider HKL is unmixed. In case of normal FCC, unmixed. If in case of normal FCC, if it is unmixed, we should always get intensity, right. In this case, there is an additional condition on top of that. For unmixed condition, that additional, what we can write, the structure factor F equals, this part is anyway giving me 4, if you remember, if it is unmixed, plus now I have this FNA plus FCL and this additional term E pi I H plus K plus L, right. This one is similar to the body centered condition. So, if you remember the body centering, there if we get this H plus K plus L even and odd, depending on that we were getting some intensity sometimes, and sometimes we do not get any intensity. In this case, that won't happen, but additional condition in unmixed, if unmixed condition, if I get H plus K plus L is, this is even, then and this is odd, two conditions I am now considering. one is even, one is odd. If this is even, then the structure factor F will have 4 FNA plus FCl, right. This is what we have seen in case of BCC, that when H plus K plus L is even, this will come out to be plus 1, this entire thing will come out to be plus 1. So, this ultimately will be FNA plus FCl, whereas if it is odd, then this will be 4 into FNA minus FCl. Okay. So, that means we will have a modification in the intensity depending, even if it is an unmixed one, depending on that whether H plus K plus L even or odd will have a mixture or will have some modifications in intensity for an NaCl structure. So, let us now consider or let us now compare this pure FCC and sodium chloride structure, and this will be far more clearer now. Okay. So, what we will be taking now, let us say 111 reflection. Okay. So, 111 for normal FCC is this one, the highest intensity peak, first and highest intensity peak for a regular FCC. This is a regular FCC case, regular FCC 111 is the highest intensity and the first peak. Okay. What will happen in case of an NaCl structure to the 111? It is an unmixed, fine. Okay. So, definitely I will get some intensity, but again if I look at this H plus K plus L condition, this is coming out to be an odd number. So, ultimately for this one I will get F equals FNA, sorry, this 4 will be there, into FNA minus FCl. This is the structure factor for 111 in case of NaCl, whereas in this condition structure factor for 111, same 111 plane, structure factor, this is the same type. So, simply this is 4F square, whereas in this case this is 4F, this 4 Na minus, sorry, this will not be there, F equals 4F, in this case F equals 4 into FNA minus FCl. So, this is the difference. So, definitely the intensity of these two will be different, or at least the expression is different. But if I consider, let us say something like 200 planes, right, 200 in this case, again it is an unmixed and H plus K plus L is here, it is even. So, F in this case will be 4 into FNA plus FCl. Okay. And here the same thing, here F will be always the same, always 4F square. That here there is no difference, no modification is happening. Whatever the this one, of course, the intensity of this 111 peak and 200 peak will be changing because the atomic scattering factor of 111 plane and 200 plane is different. That is why 111 is the highest. If you remember this atomic scattering factor, the way atomic scattering factor was changing with sin theta by lambda. So, sin theta by lambda for 111 peak and this is possibly for 200 peak. That is completely different. That is why 111 peak in this case will be the highest, 200 peak intensity will be lower for a simple FCC. But if you look at the NaCl structure, now 111 peak will have a lower intensity compared to 200 peak, because in case of 111 peak the intensity is FNA minus FCl, whereas for 200 peak it is FNA plus FCl. So, this kind of a modification in the intensity will happen because of this additional restriction. Not only unmixed, it has to, then we have to see whether it is even or odd, H plus K plus L is even or odd, and this is the kind of, if you go for a complex crystal structure, this is the kind of additional conditions which will come, which will modify the intensity and sometimes which will remove certain intensity from certain planes of at all. Okay. So, this is NaCl case, you can go on and derive such expression for many other crystal structures. So, we will be stopping with our discussion about structure factor here, and we will be moving towards some other kind of factors. But for that, the first thing we will be seeing is basically the intensity of a real specimen in this real X-ray diffraction specimen. So, if you see that normal FCC structure, so this is a normal FCC structure where 111 plane should have the highest intensity. If it is just a regular FCC, I am not even considering NaCl or any kind of complex crystal structure, I am just pure and simple FCC single element FCC structure. So, 111 should be the highest peak, 200 should be the next highest peak, and so on and so forth. Okay. But if you look at an real specimen, this one is for an example of FCC aluminum alloy, basically aluminum copper type alloy. So, in aluminum copper type alloy, which is a real specimen, not even a powdered specimen, this is a powdered specimen, this one is, and both of them are taken at room temperature. This is silver powder, whereas this one is aluminum solid specimen. And you can see that 111 intensity is almost comparable to the 200 intensity here, and even if you look at 220, that intensity also is not that different. And what another thing you can notice is the intensity decrease in the background, that also is very much apparent here in case of a real specimen. So, that means basically what this means is the intensity, there are much more factors, there are many factors other than the structure factor or atomic scattering factor and so on. Other than those factors, there are many other factors which are responsible for modifying the intensity of a real X-ray diffraction pattern. So, there are basically 6 factors in general for all, if we consider all different type of X-ray diffraction patterns. So, there are at least 6 different factors which are responsible for modifying or for determining the intensity of any real diffraction pattern. So, this is structure factor, we have already discussed about that, and structure factor basically contains, or structure factor basically covers the atomic scattering factor on all of these things. So, structure factor is of course one of them. Multiplicity factor, this is also another very important factor, and which is related to the crystal structure or atomic arrangement within the unit cells. This structure factor and multiplicity factor, these two factors are crystalline, that means related to the atomic arrangement of any within any unit cell. Third one is the temperature factor, purely the atomic vibration because of the temperature related to that, we'll discuss about this. Polarization factor, we have already discussed, if you remember that intensity when we were discussing about the intensity coming out of for an entire atom, and there we were from electrons, the intensity of an electron at a certain point IP, and there IP equals I naught into 1 plus cos square 2 theta by 2, and we said that 1 plus cos square 2 theta by 2, that factor is called polarization factor, which was simply entering in the diffracted beam intensity because the beam is not polarized. If it is polarized, then this factor won't there. So, that is the polarization factor, which is related to the geometry of the diffraction or related to the beam itself. Similarly, there is another factor which is called Lorentz factor. We will not discuss into that. Lorentz factor is again a geometrical factor which enters because of the geometry of this entire detection system, the position of the detector and all. We will not discuss. Together, Lorentz and polarization factor, basically many a times they are clubbed together and called Lorentz polarization factor. We will not discuss. Absorption factor is related to the X-ray absorption. We will briefly discuss about this, but not in any great detail. Basically, structure factor, multiplicity factor, these are very important. Temperature factor also. So, when we calculate the intensity of a diffracted beam, we should always start with the structure factor. If structure factor is saying that certain intensity will not be there, it will not be there at all. So, structure factor is, out of all these factors for a crystalline material at least, out of all these factors, structure factor is the most important factor, and structure factor is primarily responsible for the intensity from any diffracted beam, from any crystallographic plane. If that structure factor says it is a forbidden reflection, that will not be affected by any other factor. Only if structure factor allows, permits the diffracted beam to have certain intensity from certain crystallographic plane, then only the other factors will modify the intensity of this plane. Okay. So, that is most important is the structure factor if you want to calculate, if you want to analyze the intensity of an X-ray diffracted beam. Okay. and this intensity again will decrease on specific X-ray diffraction method. For example, Laue diffraction, there the calculation of the intensity of the diffracted beam is very difficult, and it also depends on the sensitivity of the film over which this X-ray diffraction pattern is calculated. So, we will not go into there. Mostly at the present day, we most important or most popular diffraction, X-ray diffraction method is powder diffraction method or solid sample diffraction method, and we will be just discussing about that, and we will be discussing about those factors which are where monochromatic radiation is used and we are getting the intensity, X-ray intensity in a detector, in a real detector. There we will see how the different factors will modify the intensity of this. So, first of all is basically the multiplicity factor. As I said, this is related to the atomic arrangement. This is basically related to the multiplicity of atomic plane, but this we will be covering in the next class along with the temperature factor. Thank you.